So we talked about matrices of numbers. We talked about what can we perform upon matrices, which are called row operations. Um, and with these row operations, we're able to get matrices and put them in certain forms. And we had a homework problem where we differentiated between echelon form, reduced row echelon form, and row reduced echelon form. And in completing these elimination and creating these different forms of the matrices, we see the connection that there exists with um, matrix equations. Like we're able to now a little bit more systematically solve linear systems of equations through row reducing a, um, a matrix of numbers where these numbers are coincide with the coefficients of the original linear system. And then we started getting to the nitty gritty details of operations that are applicable to matrices. Of course, we can add to matrices, we can subtract to matrices as long as the dimensions, the number of rows, the number of columns are identical. We're also able to perform scalar multiplication, which just means we multiply a number by a matrix, a scalar, which is a number. We can multiply by matrix, and what that means is we multiply every entry in the matrix by that number. And a more complex operation is the matrix multiplication one, which we had to make sure, and this is one of like the ones that is very unique to linear algebra with matrices, and that's multiplying the row per column. So the first row and the column, so the first matrix and the second matrix, or I should say the left matrix and the right matrix. You take the row from the left matrix, and then you take the column from the right matrix, and you correspond each entry. You multiply the corresponding entries and you add them up, and that is known as the dot product. But don't worry about the terminology of that, but that's something similar to what the dot product does. And so in order to multiply two matrices, you have to be consistent with the number of entries of the columns with the number of rows. So the number of columns in your left matrix has to coincide with the number of rows of your right matrix in order for matrix multiplication to even be feasible. And so we saw that in detail. And we understood that matrix multiplication is not your typical multiplication where we are used to with numbers, right? Where this idea of commutative matrix, the idea of multiplication being commutative, where the order does not matter. In this case, matrix multiplication, it does. It's not necessarily true that you can just swap the order of the matrices, of the order of the matrices, and get the same result when you multiply them. It's not necessarily true. It's not even feasible to do that every time because of the requirement for the matrices to have in order to be multiplied together. And then we talked about the identity matrix, right? It's just a matrix with ones on the diagonal and zeros everywhere else. And that was to the extent of what we went over last, was it 2 weeks ago that we were together. So I want to continue on with matrices, and I want to go back to the fact that matrix multiplication, right? So matrix multiplication continued. Whoops, pretty chunk off. So we talked about how we multiply matrices, and I just want to stress the fact, and I mentioned this before, that what says that matrix is a linear combination. So what is a linear combination? So this word here is going to appear a lot. So let me just call this a definition here. So linear combination is a sum of products. That's that's one way, very bluntly, to put it. It's a sum of products. So when we see something like this, right? So an example. So if we say 1, 2, 3, 4, 0, 2, and then 0, 1, 1. If I multiply this by, so this is a 3 by 3 matrix, right? And I multiply this by what we call a column vector. So a column vector is a matrix that has one column and multiple rows. So this is called a column vector, which is just, again, a matrix with one column. So it's a matrix with a single column. So then let's say I call this, I don't know, 201. So how do we multiply this out? We know, right? Row 1, column. Row 2, column. Row 3, column. And what I want to show you guys, this is 2 times 1 plus 0 times 2 plus 3 times 1. That's the first entry. The second entry will be 4 times 2 plus 0 times 0 plus 2 times 1. And then we get 0 times 2 plus 1 times 0 plus 1 times 1. Now, we can do this and we get an answer at the end, which we'll get. But I just want to stress the fact that if you recognize we can separate these things, right? We can separate this as 2 times 1, 4 times 2. I'm just going to write this as 2 in the front. 2 times 4, 2 times 0, right? This is a column vector plus 0 times 2, 0 times 0, 1, 0 times 1. It's another column. And then a vector, and this is the last one. 1 times 3, 1 times 2, 1 times 1. And then I'm just rewriting this in a way that looks like the following. So it's 2140 plus 0 times 201 plus 1 times the column vector 321. And if you pay close attention to what just happened, we went from here to here, right? And then what do we notice? We notice that the 201 corresponds with the entries of the column vector. And we notice that these column vectors that we have here are exactly the columns of our original matrix. So here we hopefully see that matrix multiplication is a linear combination of the columns. In the matrix, in the left matrix, or of the left matrix. So that's another way to think about matrix multiplication. So then how do we generalize this? Right? Does everybody see that? Is that clear? That when you perform matrix multiplication with the matrix with one of the column vector, with a column vector, it's a linear combination of the columns. So you get two. Yeah, right? Is that clear? So then if that's the case, right? If that's the case, then we can visualize matrices in the following manner. So generalize this. Generalize matrix multiplication. So if we have A times B, right? And let's say A is M by N, and then B is N by P, right? So what we can do is we can consider this as A multiplied by, and then we have B. And we're going to call B1, B2, B3. And then we have how many of these? We got P of them. What did I just do? I took the matrix B and represented it as columns. So this is my first column of B, my second column of B, my third column of B, and my pth column of B. So I'm considering this matrix multiplication as what? The result is if I take the matrix A, the first column of my product of A and B is the same thing as taking the matrix A and multiplying it with the column vector B1. When I perform this operation, I get the first column of my product. And then the second column is the same idea, A, and then I get what? B2. All the way to A, BP. Again, it's just a visualization or a different understanding of matrix multiplication. When you have two matrices that are being able, where the inner and the dimensions match up, you can perform multiplication. Instead of just considering as a way of corresponding the rows and the columns, you can also consider it as taking the columns of the right matrix and performing matrix multiplication to the left matrix, and you get these columns. So that's one way to consider, to think about matrix multiplication. Okay, you can also consider it from the perspective of rows, but we'll just leave it as columns for now. Okay, so that's matrix multiplication, and we talked about augmented matrices. All right, so we'll go with this. So there's a few more things I want to talk about with matrices. One of them are called transpose, the transpose of a matrix. So there's a bit more terminology now. So what is the transpose of a matrix? So given a n by m matrix A, the transpose of A, so this is my transpose, and we denote it by A with the denote it by A with the T as a superscript. It's not an exponent. So A with the T on top. So this represents the transpose. It is the matrix that interchanges the rows with the columns, the rows and the columns of A, and has the dimension of m by n. So that's what the transpose is. It's nothing out of this world. What you're saying is the rows of A now become the columns of A transpose. So simple example, if I consider A to be 2, 3, 4, and 5, 1, 2, right? So this is a 2 by 3 matrix. You have 2 rows, 3 columns. So then what would be the transpose? Well, the transpose will be consistent. So A transpose would have a 3 by 2 dimension. And so now the rows of A become the columns, right? So this will be now what? This would be 2, 3, 4. And then we would have 5, 1, 2. So what happens? The first row became the first column. The second row became the second column. And that's it. And that's the extent of what a transpose is. Of course, you can do other examples. If you have B, for example, and you have what's called a row vector. So we have column vectors and row vectors. A row vector is a matrix with a single row. So if you have only one row in a matrix, it's called a vector, a row vector. If you have one column, if a matrix has only one column, it's called a column vector. Okay, so if I have 1, 0, -1, then B transpose, and this is going to be a what? A 1 by 3 matrix. This is going to be a 3 by 1 matrix. So this row vector, when you transpose it, becomes a column vector. And the column vector is 1, 0, -1. So everybody hopefully finds this straightforward with the definition of a transpose. Okay, so then how do we generalize this idea? So what's the general notation for transpose? So if I take the, if I want to know what the ith j entry is of A transpose, just take the entry of A and swap it with, take the jith entry. So what this is saying is take the entry in A and just interchange the rows with the column and the column with the rows. And that will give you the new entry in A transpose. So that's the notation with that we normally tend to use in general though. Okay, so that's what the transpose is. You just swap, change the rows to the columns and the columns to the rows. So that it does become important. So that's the transpose. And then associated with this, we talk about the trace of a matrix. Okay. But let me just say, before we talk about this, I just want to note something. Note. There are two things that we like to discuss in terms of differentiating matrices, and they're called square matrices. For right now, this may not be so important, but it will eventually become important because we'll be dealing with a particular kind of matrix. So we have square matrices versus non-square. Eventually, it will matter what kind of matrix you have because certain matrices, you can't apply certain things. So like, for example, when we talk about determinants, it makes no sense to talk about the determinant of a non-square matrix, but it has all the sense in the world to talk about the determinants of square matrices. So in order to talk about the trace of a matrix, I have to talk about what's the difference between a square matrix and a non-square matrix. A square matrix just means that you have the number of rows equals number of columns. That's it. And a non-square matrix is the number of rows does not equal number of columns. That's important. So for example, this matrix A here is a non-square matrix. Why? Because we have 2 rows and 3 columns. The number of rows do not equal the number of columns. And when we talk about the square of the trace of a matrix, we're only talking about square matrices. So only applicable for, so this is only applicable for square matrices, this idea. So the trace of a matrix is simply the sum of the entries on the, so I should say, the sum of the diagonal entries of a square matrix. Equals the trace. Denoted by, and we denote this by, we usually call it TR of A. So if I want to find the trace of a matrix, I just add up the diagonals and we use TRA. So for example, I need a square matrix. So 1, 2, 5, 4, 0, 5, 2, 7, -8, 9, right? So then what are this is a square matrix because it's 3 by 3. And the diagonal matrix, the diagonal matrix entries we're considering, we have two diagonals here, right? But the diagonal that we're considering is this one. We don't consider this as a diagonal, the one from the left corner to the right, the left bottom corner to the upper right corner. We consider these, the one from the upper left corner to the bottom right corner. We consider this as our diagonal because it's consistent with a sub 1, right? The first row with the first entry, the second row with the second column entry, and then the third row with the third column entry. So it's that. So what's going to be, if we call this A, what's going to be the trace of A?
Would it be 15?
Right. Add them up. 1 plus 5 plus 9, and it will be 15. And again, right now you're like, wait, doesn't sound like a big deal. But these are just like tools, concepts of matrices that will become eventually useful. So we're just becoming more acquainted with matrices.
Professor, can you repeat why we don't consider the other diagonal one more time? I didn't get that.
Well, in general, right? You start to see that this is the diagonal that we care about because this is where the pivots occur, right? When we talk about row reduced echelon form and all that, the pivots occur on this diagonal. They don't occur on this diagonal. So in a way, we don't really care so much about these numbers. What are the significant numbers are the ones that are on this diagonal because of the very nature of how we perform row operations on it. So when we talk about diagonals, the diagonal entries of a matrix, we're not talking about the diagonal that goes from the bottom left corner to the right left top right corner. We care about the upper left corner to the bottom right corner.
Okay, thank you.
So they call this the main diagonal. So I'll make this a little bit more generalized. So what's the general notation for the trace of A? So if I have A, right, and I should say this is a n by n matrix because it's a square matrix, right? So then what's going to be the trace of A? How would I write this in notation, in general notation? I would take, it's the summation of the diagonal entries, and the diagonal entries are the ones that are the first row, first column, second row, second column, third row, third column, fourth row, fourth column, all the way to the nth row, nth column. You add these up and you get the trace. Makes sense? That's how we generalize this idea of trace of A. Okay. And then just to briefly note, the entries of the main diagonal of a matrix A, I'm just going to call it, it's n by n, is of the form, sorry, it are of the form A sub II. So that's when the indices are the same. That's what it means to be the main diagonal, or entry on the main diagonal. Your row, the number of your row equals the number of your column, which just means you're on that diagonal. Okay, so that's what we have. We have the trace now. The trace only applies for square matrices, and you add up the diagonal entries, and that will give you the trace. Again, it's a very simple computation, but eventually you start to see why we even care about considering the trace. And the transpose just means you take any matrix, it could be square or non-square, So this is applicable for both matrices that are square or non-square. You can apply this also to square matrices. So let me just write that. It's applicable for both square and non-square matrices. And the transpose just means you switch the rows and the columns. That's it. Okay, so far, just a bit more, a bit more techniques, or I should say terminology about matrices. Now, I want to do something simple. With linear algebra, it's such a vast field, and it's both theoretical and it's both very applicable. So far we've been very concrete with all the things we've been doing. We've been considering several examples. I've done a little bit of generalization, right? A little bit of it. I hinted. Now, what makes linear algebra very special, at least in my eyes, is that when you take linear algebra, you start to see mathematics in a different lens, under a different lens. It's much more sophisticated. It's a bit more mature. And what makes it mature is this idea of proofs, right? So proofs is an inherent element of learning linear algebra. And that's something that maybe not too many of you have so much experience with, and that's okay, because that's what happens when you start to learn mathematics at a higher level. We care a lot about proofs. So I want to prove the following. Prove if A and B are n by n matrices, so they're both square, right? Then usually that's how it works. Like I have a statement, I have an if statement, and then I have a then statement, right? You guys have, for those of you who do computer science, the if else thing, right? The if and the else for like the loops or whatever. You guys know more of that than I do, but it's kind of similar. It's if this is true, then the following is true. So if A and B are square matrices, then can you prove to me that the trace of A plus B is equal to the trace of A plus the trace of B? It's a simple statement, nothing crazy. I'm telling you, I'm saying if you have two square matrices and you take the sum of those two square matrices, and I want to find the trace of that sum, it equals the trace of one plus the trace of the other. Now, does anybody have an idea of how to prove this? Yes, Baldwin.
I forgot the name of the proof, but we basically just plug in the numbers.
What do you mean?
Think,
Plug in what numbers?
Never mind.
Okay. Anybody else? Proof by induction? Yeah, that's a proof by induction. That might be a little too much, firepower there.
Yeah, that's what I was thinking at first.
Because you see the n, right? You see the n, so then you're saying, for those of you who are familiar with proof by induction, it's a lot of these statements with the n, right? And then the n plus one, the inductive step, and then if you prove that it's true for some n, and then you prove that it's true for the n plus one case, then you prove it for all cases, such cases.
Yeah,
right.
That's exactly what I'm saying.
Yeah. So then that is applicable here, but even a little bit simpler than that.
We can use this the summation definition to since we know that summation is commutative, not commutative. I forgot
Summation
the
is
property.
commutative. It is commutative in matrices. It is
Right,
commutative.
right,
Yeah.
but I didn't mean commutative. I meant a different word, I think, because the summation because I would be looking at the summation of it would be a sub I plus a plus b sub I equals a sub I plus b sub I, and
Yeah,
so that
I
I
think
think that's it, right?
right. It's something as simple as that. I think Tosif, did you have your hand raised?
Yeah, I was just gonna say, can't we just like add like the individual elements, like how we would with matrix addition, and then compare them to the trace?
Right. So then, but how would you do that? So like if I say, so let A plus B, right?
Mm-hmm.
How would you do that?
Oh, okay. I didn't really have like a general like statement in mind. I was just thinking like if we had a matrix A and B, like specifically I could do it, but I don't really have a general statement.
Right. So then that's what I wanted to get at. So when you prove something like this, right, we're proving a generality. So choosing a specific case shows that what you proving is true. In a particular case, though, I want to prove it for all such cases. So that's where the notation comes in mind. So when we do A plus B, right, what are we saying? We're saying that what? What are we saying when we do A plus B? Remember how we denote A? What is A? Isn't A the same thing as saying like A I J? And then B, we take all the ith jth entries, and then when we add them up, what is it that we're doing? We're taking the ith jth entry of A and we're adding it to the ith jth entry of B, right? That's how we generalized addition, correct? So that's nothing crazy, right? So so let me just say this: the A plus BI, so what am I saying is the ith jth entry of the sum A plus B is given by this notation, A plus B parentheses ij, right? To get that ijth entry of A plus B, I take the ith jth entry of A and take the ith jth entry of B. And that's it. So we say, let this be true, right? This is true. Okay. And then what do we know? We know that what? We know that. What's the trace then of A plus BI? What's the trace of A plus B? Does anybody know how do we go from here now?
A plus b sub ij.
So it's taking the A plus B, right? But we're not taking the sub ij, you say. We're taking the diagonal entries. We're taking the diagonal entries of that sum, right? Which is the same thing as saying what? AII plus BII. We're taking the diagonal entry of A, diagonal entry of B, and we're adding them, right? Do you guys see that? So the trace of A plus BI, when we take this random square matrix A and a random square matrix B, same dimensions, we're taking the trace of them. It's like taking the diagonal entries of A plus B, right? That's what this is saying. This is saying the diagonal entries of A plus B. Diagonal entry of A plus B. In doing so, what we just did was we took the diagonal entry of A plus the diagonal entry of B. And then we're taking a sum of these. So we can rewrite this as a summation notation of A sub II plus the summation of B sub II. But then what does this represent? By itself, what does that represent?
Trace of A.
It's trace of A. Again, this is kind of a simple thing, so I know it kind of seems like oh duh, right? But it's important to be able to write these kind of statements. And then the next one would be the trace of B. So I was able to explain this in generality. Do you guys see that? So then what did I just show? What did I prove? I showed. What did I show? I show that the trace of the sum of A plus B is equal to the individual traces of the matrices, because I just went line by line and I showed you in generality. So then how do we usually end a proof? We usually like either create a little box and circle it, or we write the words QED, which in Latin means what is meant to be shown. So have you guys seen proofs like this? This is a simple proof, it's not complicated. But something like this, I think maybe in discrete math or something like that, right? They do a lot more
Yeah.
proofs. Yeah, different kinds of proofs, proofs by contradiction, proofs by induction. So good. So linear algebra has tons of proofs, tons. So for those of you who like proofs, you're in the right place. For those of you who need a little more help, this is also the right place, because we're going to be doing a lot more proofs. And most of these statements and theorems in linear algebra require to understand the proofs. Again, this is a simple statement. It kind of is obvious. Sometimes it's not as obvious. Any questions about this? We're good with that. So the trace of a sum of matrices is equal to the individual traces, the sum of the individual traces. Makes sense. Okay. So we talked about traces, we talked about transposes. Now let's talk a bit more about matrix multiplication. There's still a lot to say about it. And there's something called the associativity of matrix multiplication. So even though matrix multiplication is not commutative, meaning that the order of the matrices does matter, and it's not necessarily the same when you rearrange the order of the matrices, associativity still holds. Now, what does that mean? That means that if I have, for example, 3 matrices, right, and I'm multiplying them, and let's suppose that the dimensions of all 3 matrices work out. Then if I multiply BC first to get a matrix and then multiply it to A, it's the same thing as multiplying AB and then multiplying it by C. That's what associativity means. So this holds for matrix multiplication. You can multiply AB first and then C, or then multiply BC first, then A. So matrix multiplication is associative. Okay. Okay. Okay, so then we have that. Now, we talked about row reduced echelon form a lot. And there's one thing I want to just make mention, and this is a theorem. If R is the row reduced echelon form of a matrix, then either R, and this is a square matrix, sorry, is a form of a square matrix. So if you take a square matrix and you perform row operations, Gaussian elimination, so that you get the row reduced echelon form, RREF, right? then the row reduced echelon form can either be two things. Then either R is the identity matrix. We denote that by I, or it has at least one row of zeros. So there's only two possibilities when you perform row reduced echelon form, or when we perform Gaussian elimination upon a square matrix. You either get a matrix that's an identity matrix, right? That's what we've been doing in the beginning. We saw how the matrix, the square matrix, when we reduced it, when we put it in row reduced echelon form, we either got ones all on the diagonal and zeros everywhere else. That's the identity. Or we start realizing, wait a minute, there was like a row of zeros that just popped up every time. So that's one thing about row reduced echelon form. And associated with that are also two ways to distinguish square matrices. So there's two types of square matrices. So again, this is all about square matrices now. We're kind of heading into the world of square matrices. Two types of square matrices. So there are what are called singular versus non-singular. So the terminology starts to creep up on you. You guys see it? Okay, sorry, it was lagging on my end. So we have singular matrices versus non-singular matrices. What does that mean? AKA, right? There's another way to write this. We have what are called non-invertible matrices versus invertible. I know it's kind of clunky. So singular matrices are called non-invertible matrices, and non-singular matrices are called invertible matrices. There's two kinds of matrices that we can separate as into groups. Now, what does it mean to be invertible? What does the word invertible mean? At least in the case of matrices. So if you know what an invertible matrix is, then you would know what a non-singular matrix is. And if you know what non-singular and invertible matrices are, then you would know what singular or non-invertible matrices are. So I'm going to write the definition of invertible. So an invertible matrix this is going to become very important throughout the next few lectures. It's the idea of inverses, because with inverses, that's how we solve linear systems when we talk about the matrix equation. So an invertible matrix B, I should say an invertible matrix, and again, invertible matrices only apply to square matrices. Again, this is only about square matrices. So an invertible matrix A is called invertible if there exists a matrix B. So again, we're only dealing with square matrices. So I'm gonna just make sure I'm gonna specify this is n by n. This will also be n by n. Okay, so there's gonna be a lot of n's here. So a square matrix is invertible if there exists another matrix such that when you multiply A with B, it gives you the identity. And when you multiply it from the other way around, it also gives you the identity. And what we do is we denote, so note, we denote the inverse of A as A to the negative. It's not, this is not a power. It's just notation. It's notation for matrices. Okay, so when you have an A and you have a -1 as a superscript, that indicates inverse. So another way to write what we just wrote, A times B equals I, B would be A inverse. So then we would say B is equal to the inverse of A. So if you have a matrix that when you multiply with the matrix A gives you the identity, and if you switch the order of operations, it also gives you the identity, then that B value is that B matrix is the inverse of A. And if such an inverse exists, then we call A to be non-singular, or in other words, invertible. Make sense? So we're starting to go down the rabbit hole with this. So we have matrices that have non-square, and there are two kinds, right? There's square and non-square. Now we're going to be particularly concerned with the square matrices. And now we're going into what is called singular matrices versus non-singular matrices, or non-invertible versus invertible matrices. And we care about matrices now, whether or not they have an inverse to even begin with. For those matrices that have inverses, which means that you multiply them and you get the identity, for such matrices, they're called invertible. And for those that don't have an inverse, they're called non-invertible or singular matrices. Okay, so another way to write this, just a little bit clearer, would be A times A inverse equals A inverse times A, which equals identity. Now, there's a theorem about the uniqueness of inverses. So what that means is if B and C are inverses of A, then B equals C. This is one way that mathematicians tend to prove that something is what's called unique. And remember we talked about unique, what it means to be unique? What does it mean to be unique? Anybody, what is it? Remember we talked about this, like I think the first lecture, second lecture. What does it mean to be unique? Something that was unique. It's not mere, yes? Nothing is like it, which means that there's only one of them. So when we talk about the uniqueness of inverses, we're saying that when you have an inverse, there's only one. There's not multiple. That's what it means. Now, we can prove this. Does any? Yeah, it's distinctive, but not just distinctive. There's only one of them. So only one. Remember, unique means there's only one. So that's exactly what I'm saying. If there were two of them, that's what they're saying. If B and C are two different inverses for the same matrix A, then the reality is that both of them were actually the same. They're actually the same. So how do we prove that? How do we prove that? Well, we use what we were given, right? B and C are inverses of A. So if that's the case, so since B is an inverse of A, then B times A, doesn't that equal I? That's what it means to be inverse. When you multiply them, you get an I, right? It doesn't matter what I do, A times B or B times A. And then you say since what? Since C is an inverse of A as well, then multiply the equation above by C. So I'm gonna take my equation B times A, right? And I'm gonna multiply it by the right by C. Now, because I'm multiplying by the identity, I times C is just gonna give me C, right? And then what happens here? By associativity, what can I do? I can rearrange the order of the multiplication, right? But then what is A times C gonna be? B times C, A times C is the identity since C is the inverse of A. But then what is B times the identity? It's C. So then what did I just prove? I proved that if I do have two different inverses, they really are just the same, one and the same. So inverses are not different. You can't have more than one inverse. There's only one unique inverse. That's what this means. Does that make sense? Okay. So far we talked about square matrices, the differences between non-singular, singular, meaning that they're invertible matrices, and they're non-invertible matrices. So now we're going to be very, sorry about that. We'll be concerned with whether or not matrices are invertible. Okay. Now let's look at a specific kind of matrix, the 2x2 matrix. So I'm going to give you a matrix. I'm going to call it A. And I'm going to have these letters that represent the entries of A. Now I want to find, if it's possible, I want to find the inverse. So that when I multiply them with A, either way, I get the identity. Now, how would I do such a thing? And let me just tell you, I'm going to rearrange these letters here in such a way that when I multiply them out, I'm able to get ones on the diagonal and zeros everywhere else. So without making it too crazy for you guys, this is what the inverse looks like. This is my inverse. So for any 2x2 matrix, if it's invertible, then the inverse has this form. Right? So then how am I sure about this? How am I sure about this? Well, I can multiply it out. What would be A times A inverse? What would that look like? It would be AB, CD. And I'm going to multiply this by 1 over AD minus BC. Multiply that by D minus C negative B A, right? Now, this number here, this is a scalar. Since it's a scalar, I can move around this scalar around the multiplication. I can't move or change the order of matrices, but I can change the order of scalars. So what I could do is I can rearrange this as 1 over AD minus BC, again, since it's the scalar. But the order of the operations of the matrix, I can't change. I can't. Now, what does this look like? When I multiply it out, first row, first column, right? What is that gonna look like? This is AD minus BC. That's the first row, first column. Then first row, second column, what is that gonna look like? Negative AB plus AB. First row, second column. Second row, first column, what is that gonna look like? CD minus DC. And then the last row, last column, what is that gonna look like? Negative BC plus AD. What do you realize? This becomes 0, this becomes 0. So what am I left with here? I get 1 over AD minus BC. This is AD minus BC, 0, 0. And this is, I can rearrange this as AD minus BC. I don't know why I do that. And I'm multiplying this by a scalar 1 over AD minus BC. And when I multiply by a scalar, what am I multiplying every entry by? That same scalar, right? So really I get this. I get AD minus BC over AD minus BC. Of course, 0 divided
And
by
you get
anything
the
is 0. Say it again.
No, it was just clicking. Now you get the identity you mentioned.
Yeah, now you get the identity, right? So all I just showed you was that if an inverse exists, this one would work because I get the identity. I get 1, 0, 0, 1, which is the identity. And if you want, you can do it the other way as well. You can rearrange A inverse with A, and you get the same thing. Again, this is a formula in a way you can think of it, right? This is a formula for the 2 by 2 matrix. If it were to be invertible. Now I'm saying if. How do we get there? Great question. Great question. How do we get there, right? That's hopefully you'll see how we can get there a little bit later. But right now, just take that as what it is, the formula for the inverse. And there's something about if it's possible. So if A is invertible, so I should say that. If, it's a big if A is invertible, then I should write this. A inverse is its inverse. And of course, we know what inverse is. A times A equals A inverse times A, which equals identity. Now, Baldwin, you had a question?
Yes, I'm just trying to like wrap myself around the terminology. So this
Yeah.
would need to be a square matrix.
2 by 2.
then it'll be-
We're dealing with a very specific square matrix. It's a 2 by 2 square matrix.
Okay, and then it's non-singular, right?
We're supposing that this matrix that's square 2 by 2 is invertible, which means it's non-singular.
Okay, gotcha.
Suppose that this were so, the inverse would have this form. And I just showed you why. So I showed why. Why is this the inverse? Well, if you multiply two matrices and they give you the identity, then it's an inverse. That's what it means to be an
Okay.
inverse, right? So I showed you,
Thank
hey,
you.
this is a general matrix. Hey, this is the inverse of the said general matrix. When I multiply them, I get the identity. Henceforth, they're inverses.
Okay, makes sense.
But not every square matrix is invertible. And then I'm asking, does anybody see where this can go wrong? Where can this formula go wrong?
When
If you look at
AD
the
minus BC equals 0.
That's the problem. So then this is like a caveat, right? So note AD minus BC does not equal 0. So then now this becomes a condition. If I have a 2 by 2 matrix and AD here, right, are specific entries, they're the main diagonal entries. If the product of the main diagonals subtracted with the product of the off diagonal or the other diagonal, if that difference of those two product of those two entries, if it equals 0, then it's not invertible. If it doesn't equal 0, then it is invertible. Do you guys see that? So now there's going to be a connection with eventually what we're going to be concerned with, which is called the determinant. But for now, don't worry about that word too much. So now the numbers that you have in entries matter a lot with whether or not an inverse exists. Okay, so maybe we should look at a specific example. And why don't we do this? So we're going to consider the case where we have a 2 by 2 non-singular matrix. Non-singular, in other words, aka invertible. I know the terminology here came in quite fast because now you have two different words that mean the same thing, and they're both kind of like, wait, what? Invertible? That's one thing, and then non-singular sounds like it's another thing, but it's exactly the same. It's just two different words for the same thing. So 2 by 2 non-singular matrix, what does that mean? Means that what? Means that AD minus BC does not equal 0. That's what it means. So eventually what's going to happen, guys, is you're going to have what are called equivalent statements. Like, I'll give you an example. When you have parallel lines, right? What's an equivalent way to say two lines are parallel?
Like same slope or
Exactly. So then when you start to say, hey, two lines have the same slope, what are you really saying? Two lines are parallel. And then you start saying, is there another way to say the same thing? Well, Mir just said it. If you have two lines that never intersect, then what does that mean? The two lines are parallel. What does that mean? That means that the two lines have the same slope. So all of those statements that I just said are identical. They're the same. Eventually, we're going to be listing out a whole list of equivalent things. So for example, when we say a matrix is invertible, let me just specify. When we say that a 2 by 2 matrix is invertible, what does that mean? It means that an inverse exists. What does that mean? That means that AD minus BC does not equal 0. So all of those statements now are equivalent. One implies the other. And there's going to be a list of a whole slew of them as we build up more concepts and techniques to this. So invertible matrix means it's non-singular, which means an inverse exists, which means AD minus BC does not equal 0. So if AD minus BC does equal 0, then what does that mean? The matrix is non-invertible, which means that the matrix is a singular matrix. Do you see that connection? So now you're going to have to start doing that now on the fly as we continue on. So then can we create a 2 by 2 matrix that's non-singular, meaning that's invertible? Well, then take two numbers that when you multiply A and D, right? Like I could just make them up as we go. 3 times 1 minus 2 times 5, for example. So then I'm just going to create this matrix right now. A is equal to what? 3, 1, and then 2, 5. This is a 2 by 2 matrix that I just decided to create. What I know is that these numbers, when you multiply, you get 3 minus 10, which equals -7. It doesn't equal 0, so I'm good. So what does this mean? Immediately what? A is invertible, which means that what? A inverse exists. Now, what is A inverse? Using the formula, what do we know? It's 1 over AD minus BC. And what is this? D, right? This is D negative C. So we switch the entries, DA, and then we negate the off-diagonal entries. So using this formula, what do we get? We get 1 over -7. We switch the 3, the 1 and the 3, and we get -2, -5. This, my friends, is the inverse. Or you can write this as 1, -7 2/7, 5/7, -3/7. And you can check this yourself. So check that A times A inverse equals A inverse times A, which gives me the identity. It has to work, and it does, because this is the formula, and then hopefully you'll see how we even get to that. How we even get to that formula. So far, so good, guys. We just created a non-singular matrix, and we found the inverse using the formula. Okay. All right. So then, now that we have that, let's look at an example. And I'm going to use the same matrix A. And of course, I'm going to create a matrix equation. Okay. So so what does this represent? If I do this, A multiplied by X bar arrow equal B arrow. What is this matrix equation representing? It represents this, right? 3, 2, 5, 1, XY equals 1, 1. Which also represents what? 3x plus 5y, 2x plus y equals 1, 1. That's normally we start from here, right? And then we do elimination substitution method, right? But now we're representing this as a matrix equation. Now, I'm not going to be doing the 2x2 algebra 1 way of solving it anymore. I'm going to use linear algebra techniques. What's the idea again? What's the idea? The idea is that if you have A times X, right, equals B, what's my goal? I want to find X, right? That's the goal of most of these algebraic problems. I want to find what's the variable, what's the missing piece, right? Now, normally, if this was a regular question like this, right? Let me make this a little more interesting. 5x equals 11. What would you do to figure out what X is? You would divide by 5, right? This cancels and you get X equals 11 over 5. Now, make that, let's run that back a bit. What did we really do? We multiplied by what? The multiplicative inverse of 5. And we did the same thing here. And then what happens when you multiply 5 by its multiplicative inverse? You get the multiplicative identity, which is what? And then we say X is equal to 11 over 5, right? But of course, we don't write it this way because it's kind of clunky, right? Like who writes the answer X is equal to 5 to the negative first power times 11? Like no one does that, right? But we do it here. I do it here so that you start to see, hey, I'm doing the same thing for this. But now I have different objects, more mathematical objects. I'm dealing with matrices instead of numbers. But the goal, the way in which we're trying to solve it is identical. I'm trying to find a missing piece that's being multiplied. In this case, this multiplication is not regular number multiplication, it's matrix multiplication. So it's the multiplication applied to just matrices. What do I want to do? I want to isolate X. How do I isolate X? First, I got to get rid of A. What do I need to get rid of A? I need its identity. I mean, not identity, inverse. So then I multiply left side by A, don't I? A inverse. And I do the same thing on this guy. But then what happens? What do I know? Matrix is what? Associative. So I can do this first, can I? Again, this is just the idea. Now, if I do this first, what happens when I multiply a matrix by its inverse? If I multiply a matrix by its inverse, what do I get? The identity,
Yeah, then
right? And if I multiply anything by the identity, I get that thing again. So then what is my solution? What is it that I'm looking for? This column vector here is the result of taking the inverse of A and multiplying it on the left to the column vector B. So I essentially, in a sense, solved every linear system that ever exists, as long as A is invertible. If A is invertible, find the inverse. So then the question, the crux of this problem really lies in how in the world do you find the inverses of any matrix? Because once I find that inverse, just multiply it on the left to B, and I get the answer. It sounds simple, but then the act or the process of finding the inverse can be quite problematic, especially when A gets to be a million by a million, for example. How in the world do you get the inverse of a million by a million matrix? Like, how do you do that? And then it's like, first of all, how do you figure out something is invertible or not? That becomes a question. See, now it becomes much more than just saying, hey, I get, again, starting with 2 by 2, everything seems simple. Oh yeah, this is so simple, just find the inverse. But then the moment you go to 3 by 3, 5, 4 by 4, then things get what? Like what's going on? Okay, so to solve this problem just very simply, right? What do I do? To find x inverse for our problem, I find the inverse. What's the inverse? I already found the inverse, didn't I? The inverse is what? Is 1, it's -1/7, 5/7, -3/7, 2/7. And I'm multiplying that by 1, 1. When I left multiply, what do I get? I get -1/7 plus 5/7, and I get 2/7 minus 3/7. And what do I get at the end? 4/7, -1/7. And that's my answer. This is my solution. So x has to equal 4/7, y has to equal -1/7 to solve this system that we have. Okay, so once I have the inverse for a 2 by 2 system, it's just multiplying a 2 by 2 matrix with the 2 by 1 matrix or column vector. Okay. So now every 2 by 2 system kind of seems trivial to solve, right? It's kind of like there's not much to it now. Like we know all the we know what to expect every time. Okay, now there's another theorem about the product, the inverse of a product of matrices. So if A and B are invertible, and AB is invertible, then A times B, when you take the inverse, it's equal to B inverse A. A inverse. So if both A and B are individually invertible, and the product of two invertible matrices is also invertible, then the inverse of that product is going to be the inverse of the right matrix first, left multiplied by the inverse of the left matrix that we had first. So the question is, how come? Or what would be the proof? Well, the proof is, if this is true, then what? Then AB, when I multiply it by A times B inverse, I should get identity, right? This is what I should get. So let's see if that works. So what am I saying? This here is equal to what? A times B multiplied by B inverse times A inverse. That's what I'm saying. That's what I'm proposing. What happens when I do this? Well, what do I know about matrix multiplication? It's associative, right? So as long as I can group them, it doesn't matter how I group them. So if I group these to be first, what happens when you multiply B times B inverse? I get the
Identity.
So what do I get? I get A times the identity times A inverse. But what's identity times anything? It's just that thing, right? It doesn't really matter. But what's A times A inverse? The identity. So I just showed you that if I take AB and I multiply it by the proposed identity, I get, by the proposed inverse, pardon me, I get the identity. Now, what if I do it the other way? So this is part A. I have to also show the other way, right? If I multiply the inverse first on the left side by AB, I have to show that it just gives me the identity. So I must show this. I must show this. Okay. If that's the case, then what? This will equal what? B inverse times A inverse times A times B. Do you see how we get the same kind of result? What do I do here? Associate A inverse with A, and I get B inverse times identity times B. Well, the identity is just being multiplied to something, and in a way you can just don't worry about it. It's the same thing that we multiply by 1, and you get the identity as well. So what did I just prove? I proved that the inverse of a product of matrices is equal to the individual inverses of the matrices when you reverse the order of the multiplication. That's what I just showed. And it works out with this proof. It works out that if I multiply this proposed inverse of AB, I get the identity. If I do it AB and then the inverse, and if I switch the order, the inverse first, then AB, I still get the identity. Yes, Baldwin.
Just a quick question, and this is possible because we're using the associative property of matrix multiplication.
That is correct.
Okay.
Yeah. And again, we're assuming that these matrices are, since they're invertible, we're assuming that they're square. And because the product is invertible, we're assuming that the dimensions match up. They have to match up. So they have to match up in order for this to exist. Since they're both square, they must be the same dimensions. And because that's true, then we can apply associativity. So we can associate them in a way that is convenient to us to give us what the result that we want. So now you can just move on with your life by saying that whenever you have a product of two matrices that are invertible, the inverse of such a matrix, product of such a matrix, two matrices, is going to be given by the inverse of one multiplied by the inverse of the other, but you switch the order now. Because the other way wouldn't give you, the other way, if this was A inverse, B inverse, and you try to do this, you would not get the identity. You wouldn't. Like the moment you do this, A times B, and then A times A inverse B inverse. You can't switch. You can't switch the order. You wouldn't be able to switch these because matrix multiplication is not commutative. If it were commutative, then you can switch it every time. You see that? So since it isn't, then we're stuck here. The very moment we do this, we're stuck. We can't proceed. But when we have it in this form, everything just flows nicely. So then we can generalize this point. So if we have a product A1, so tell me, what is the inverse of invertible matrix of a product of invertible matrices A1 times A2 times A3 ... A sub n is what? What would be the inverse? If I call this whole thing B, what would be the inverse?
B inverse. The A inverse times A1 inverse times A2 inverse.
Right. It would just be the just reorder them from the last one, make that the first one, and then vice versa. And then you just rearrange the order and just find the inverses of each of them. And that would be the inverse. So that's just generalizing into when you have a sum of a product of n matrices. Right? Okay.
Yeah. Can you explain B again?
So this last statement is just a generalization of the theorem that we had. We had that if we have two square matrices that are invertible and whose product is invertible, then the inverse of that product is B inverse A inverse. So the inverse of A times B is B inverse A inverse. So then the extension to this is that if you have a product of multiple invertible matrices, so not just two matrices, but let's say you have more than two. So like, let's say I have n such invertible matrices, and I take a product of the first one, the second one, the third one, all the way to the nth one. Then the product of these invertible matrices, the inverse of that product, which is B inverse, would be an inverse times a sub n minus 1 inverse all the way to a sub 1 to the inverse of a sub 1. So I'm just extending this idea from the 2 by 2, the two matrix case to the n matrix case. If I switch the order for the two matrices, right? If I switch the order to take the inverse of each, I'm gonna do the same exact thing for the multiple case. I'm just switching the order and taking the inverse of each of the matrices. Makes sense?
Oh, Professor,
Yes.
can you explain B again?
This one?
No, the top, a little.
Oh, you're talking about this one?
Yeah.
Okay, so this part B, okay. So the idea behind the proof is not really a complex proof. It's not really that elegant. It's just, if I were to claim that this is indeed the inverse of AB, then I would have to show two things. I would have to show that this proposed inverse that I'm given, or that I'm showing you, that when I multiply it to AB, I get the identity. And if I multiply it to AB in the other direction, I would also get the identity. That's what it means to be an inverse. An inverse means that if you multiply it on the left, or if you multiply on the right, the result will give you identity. So if I multiply AB by the proposed inverse, what happens is I'm led to showing you that it gives me the identity. So that works out. So if I multiply the inverse on the right, I get the identity. Now part B is saying, what if I multiply this thing on the left? It has to also give me the identity. Let's show that. And when I did that, right, I said, hey, this is exactly equal to this. So this, I get B inverse A inverse times A times B.
Oh, so the
Then-
bottom, so the bottom, so the bottom is the identity of the top, right?
What do you mean by the bottom?
B inverse times A inverse is the identity of A times B inverse, right?
Be careful, it's the inverse, not the identity. I know it sounds the same because it starts with an I, but it's the inverse. So B inverse A
No,
inverse.
no. What I'm
is-
saying is that you changed it, right? You changed the identity, right? You
This part
substituted it,
here,
right? Yeah, you substituted it.
right? I replaced it with what it resulted in. So A inverse times A is the identity. So yeah, I
And
should
then
be.
yeah, and then on the other side you multiplied by the inverse, right?
Yeah, B inverse.
Because what
Or,
so
or-
what,
we're talking about
so what
this
you
one here.
yeah, so because you did it on the left side, you gotta do it on the right, basically.
Yeah, I just showed you that either way I do it, either way I slice it, if I do it on the left or the right and right or the left, like if I switch the order of the inverses, only if we're inverses, not with any other number matrices, because matrices are not necessarily commutative when you multiply them. But when you multiply on either order for inverses of matrices, then you always will have the same result, which is the identity. And I'm just showing you that it works. I'm showing you that this indeed works. I'm showing you from here. I want to show this. So then I showed it. I showed it. I want to show this. So I showed it. They both end up with identity. So then guess what? This is indeed the inverse of A times B. If an inverse were to exist, this is what it would look like. And then all I did was I extended this to a multiple case. Make sense? Now, is it better? Clearer?
Okay, so the I and the I between the on the right side, the I disappear, right?
Yeah, the I goes away because when you multiply by I, it's like saying multiplying by 1. What happens when you do 5 times 1? It's just 5, right? So the I is like 1. It represents 1 in this world of matrix multiplication. That's why the I goes away here. But then when you multiply a matrix with its inverse, you get I back. You get I. You get 1 in matrix world of multiplication. Okay?
Okay, all right.
Okay. Okay, great. Great. All right. So we have an idea of inverses. We have an idea of why the inverse is useful. And it's useful because you can solve matrix equations now with it. Okay. So now that we have that idea in mind, I want to talk about what are called elementary matrices. Let me see. So elementary matrices are matrices that represent elementary row operations. So what are the elementary row operations? Does anybody remember? So what are the elementary row operations? There's 3 of them.
One of them is swapping the order of the rows, right?
Right. Swap row I and row J. That's one of them.
I think there was the subtracting, the adding, and the multiplication one.
There's a multiplication one, right? So multiply by non-zero constant, multiply row I by scalar C, right? So that's just multiplying one row by a scalar. We can swap two rows. We can multiply one row by a scalar, and there's one last one. It's not subtraction per se.
Adding
Substitution.
Adding
a constant multiplied by one row to another row.
right. So adding a constant multiple of row I to row J. Right. So now I'm using I's and J's now very very commonly now in my speech, because we usually denote different indices with I and J, sometimes K too, but normally it's I and J. Now for each of these row operations, there's a matrix associated with it. So I'm going to start with giving you an example. So let's start with an example of this row, of this matrix. 1, 2, 3, 0. I think 2, 1, 0, 4, 2. Actually, let's do this. No, hold on. This is 1, 0, 0, and I think it's 4, 2. There we go. So I have a square matrix, right? Example of a square matrix. So what I'm going to do is I'm going to do row operations so that I can put it in row echelon form. So make this into row echelon form, not row reduced echelon form. We're not going to do all the way. So remember, row echelon form are ones on the diagonal. Zeros everything below it and nothing else. Don't worry about anything else above. Okay, so then what's the first thing you would do with this? What's the first thing we would do? Or what can we do?
Get that middle row to have the 4 be a 1.
Yeah, we can definitely do that. But let me go a different direction. I wanna change. I wanna swap rows first. I want to swap row 2 and 3. Okay. What does that become? 1, 2, 3, 1, 0, 0, 0, 4, 2. Now, why do I do that? It's just that I want to get rid of this one. How do I get rid of this one? What am I supposed to do? Again, this is stuff that we've been doing a lot of, right?
Negative row 1 to row 2.
Right, negative row 1 plus row 2 to row 2, right? What do I get now? I get 1, 2, 3. I get 0, negative 2, negative 3, right? And then I get 0, 4, 2, correct? And then what do I do after that? So this is like saying row op 1, right? This is like saying row op 1. This is what? Row op 3. And then what would I do with this? So far I have one pivot. Yes, I think someone's gonna say something.
I was gonna say the third row, you can subtract the second row times 2 from it.
So you're gonna
Working on
do
getting that 4 into a 0.
right. So you're gonna do 2R2 plus R3 goes to R3, right?
Yeah.
So this is 1, 2, 3. This is 0. This is -2, -3. This is what? 0, 0, And then this is what, -4? Correct?
Yeah, that
And
looks
then I want to
close.
put this into row echelon form, not row reduced echelon form. So then what would I need? Make these all ones, right? So what would that entail? So this is row op what? Row op 3. And then what?
So you can multiply by the inverses of the values you want to get to 1.
Uh-huh. So what operation is this? This is row op 2, right? I'm multiplying everything by a scalar. And I'm gonna
Right.
do that as well. I'm gonna do that as well with this. So I'm doing row operation style number 2, right? So then what do I get at the end? I get 1, 2, 3, 0, 1, 3 halves, and I get 0, 0, 1, right? That's my row reduced echelon form. I'm done, right? I don't want to do this again or continue with this.
Professor, so what happens if for the calculation, you don't switch at first you don't switch what happens if you don't swap?
It doesn't matter so much.
It'll be more, well, it'll be more complex to calculate, right?
You may want to. The reason why I'm doing this is just to like illustrate a point. But if you want, you can eliminate. You can eliminate this one straight up by saying, hey, take -1, a multiple of this row, multiply everything by -1, and add it to R3, and you get rid of the 1 here and make it a 0.
That's another way.
It's another way. So the way to get to remember, REF is not necessarily unique. What will be unique will be the row reduced echelon form. And remember, we talked about this theorem just now. Every square matrix either has 2 kinds of row reduced echelon forms. Either it's the whole identity, or it has a row of zeros. That's all it can be. In this case, you start to see already, I have 3 pivots. So when I find the row reduced echelon form of this, I'm gonna get the identity. That's gonna happen.
So all 3 in the diagonal has to be ones, right? They must be ones.
Yeah, that's the goal. We make them ones. We try our best to make them one. Sometimes we're not going to be able to get every diagonal to have a 0. I mean a 1.
Yeah.
Okay, but again, this stuff you already know how to do this. I'm not showing you something new with this stuff. But what I'm trying to show you is that there's something called elementary matrices, which represents each of these row operations. Now, what I want to do is I want to find what that matrix would look like. So what would be the matrix that when I multiply it on the left to this, produces this? So I'm gonna call this, okay? I'm gonna call this E sub 1. This whole thing here is E sub 1. And then this whole thing here, I'm gonna call it the second elementary matrix. And this whole thing here, I'm gonna call it the third. And this whole thing here, I'll call this the fourth. And then lastly, the fifth. So can anybody tell me what would be E1? What do you think E1 would be? So these elementary row operations are just variations of the identity matrix. So let me help you with E1. If I want to, what rows do I want to swap? Swap rows 2 and 3. So what I'm going to do is I'm going to swap rows 2 and 3 of the identity. What's the identity look like again? You got ones on the diagonal, zeros everywhere else. Switch to row 2 and 3. What do I get? This is what I get. So when I multiply this, when I multiply E1, when I multiply this on the left, I'm gonna call this A, okay? I should have called this A. So if I multiply it by A, what do I get? I get 1, 0, 0, 0, 0, 1, 0, 1, 0. And when I multiply this, I get 1, 2, 3, right? 1, 2, 3, 0, 4, 2, 1, 0, 0. What happens when I multiply this? First row, first column, what do I get? I get 1. First row, second column, what do I get? 2. First row, third column, what do I get? I get 3. Do you see how this is untouched? The first row is untouched. Because basically what I'm saying is, hey, keep the first entry of the first row and leave everything else to be zeros. Do you guys see that?
Yes.
And then the same thing happens here, right? But look what happens here. Second row, first column. What am I left with? The first entry of the third row. Second row, second column, I'm left with the third, the second entry of my third row. Second column, last column, I get this. Do you see what just happened? And then what happens here? When I do this, what remains? So this is the elementary row operate matrix. This is the elementary matrix. Sorry, matrix. That what? That swaps row 2 and row 3. You guys see that? This is the elementary matrix. And then what would be the next one? I think the next one is a bit harder to figure out.
That's kind of cool though, how it works out.
Yeah, exactly. I know we're slowly building our familiarity with this, but then eventually this will become your bread and butter. All these matrices, all this world of matrices. This one might be a little bit harder to find. What do I want to do? I want to take the first row, add it to the second row, and make that my new second row. So I'll give you a hint. I definitely will have 1 in the diagonal, but the question will become, which ones are going to be, the rest of them will be zeros, but there's going to be one particular entry that will be non-zero, and it will not be a 1. It'll be a negative 1. Because remember, what are we trying to do? We're trying to negate the first row, add it to the second row, and make that my new second row. So now I'm going to take this guy, look, I'm going to take E2, and I'm going to apply it to this guy here. So this is really what? This is really what going to be? What is this going to be? It's going to be E2 times E1 times A. What is this here? This is E1 times A. I already got it. This is essentially what I did. I associated that first. Now, what is it supposed to look like? I'm supposed to get 1, 2, 3 for the right matrix, and then 1, 0, 0, and then 0, 4, 2. Now, can anybody tell me, how am I going to get what I want? I already know what I want, right? Don't I know what I want? I know I want my result to go from here and look like this, because I want to make this disappear and make this a 0. So how would I go from here to here? By multiplying with a very special matrix. So I already know what I want, right? I already know that E2 times E1 times A. I already know what this was going to look like. I already know this will be 1, 2, 3. This will be 0, -2, -3, and this will be 0, 4, 2. I already know what it looks like. So who can help me out here? Remember, I want to negate the first row, add to the second row, and make that my new second row. So can anybody tell me what would be the first row of this elementary matrix E E2?
Would the first row be 1 0 0?
It will have to be 1 0 0. Why is that the case?
Okay.
Because
It'll work out as the previous one we did, because it'll stay the same.
yeah, I
once
want
we
the first
multiply.
row to stay the exact same way. So then this
Mhm.
has to be 1 0 0, because then when I perform the matrix multiplication, every one of these guys here become irrelevant. And I'm only left with the first entry of every row for the second row, for the second matrix. Now, how about this one here?
That one's tricky. I don't know.
So okay, so with the same reasoning, if that first row is 1 0 0, and that leaves the first row of this one to be by itself, the last row I also want it to be the same, right? So the last row wouldn't
Yeah,
it
the
make
last.
sense to be 0 0 1?
Mhm.
Because I only care about the last entries of the third row of my second matrix. So that's why it would make sense. So then really the question is, what happens in the second row of this elementary matrix? Again, I want to negate the entries of the first row, add it to the second row, and that will become my new second row.
I got it. I got it. So would
Yeah.
it be 0 1 at the end?
0 1
Yeah,
1 like this.
0 1 1. Yes, like that. That's what I meant.
Okay, so if you do that, look what happens. This is being multiplied by this, right? So this is going to be 0 times 1 is 0. 1 times 1 is 1. 1 times 0 is 0. So the result will be 1.
Okay, yeah, don't work out.
So this wouldn't work. Anybody else?
Is it -1 1 0?
It's -1. That's right. So this would have to be -1 0. Now why? Well, it corresponds that this takes the entries of the first row. Every entry here, this number -1 here is associated with every entry in the first row. And then you're taking the second row, and you're just taking it straight up as every entry here of the second row. You're adding them up, and then you're left as the entries in the second row. So this matrix here is the elementary matrix that represents negating the first row and adding it to the second row and making that my new row. And this goes on. So now you know E2. You know what an elementary matrix would look like for a row operation of adding a constant multiple of 1 to the other. Does that make sense? And now, can you do E3, guys? What would be E3? So I know E3 times E2 times E1 times A. I already know what this looks like. This is 1, 2, 3, 0, -2, -3, 0, 4, 2. I know what that looks like. This is E2 times E1 times A. Now the question is, what is E3? What is that third elementary matrix? What do I want to do with this one? What am I told to do? I want to multiply the second row and add it to the third row and make that the new third row. So what would be the elementary matrix associated with that elementary row operation? Again, I'll give you the diagonal entries will be 1s all across the diagonal. And again, this one is associated with second R2 plus R3 becomes the new R3.
First row is still 1 0 0, right? Because it doesn't
Right.
change.
Right, the first entry does not, the first row does not change, and also the second row doesn't change, right? Because we want to eliminate the 4 in the third row. So the first row and the second row are not gonna change for the identity matrix. But then what is supposed to change? You're only including one number, that's it. Everything else is 0. And just by the way multiplication of matrices work, it's going to give you, you're going to find the right numbers to put.
Is it 0, 2, 1?
That's right. This is 2. This is 0. Second row. So this is this third. So the third row is what's being changed, right? I want the third row to change. Hence, the numbers here will be on the third row. I'm taking the second row entries and adding it to the first to the third row entries. This 2 is associated with these numbers here when you multiply it, right? When you do this here, this 2 is only associated with the entries in the second row. And this 1 here is associated with the entries in the third row. And because of the idea of the way that matrix multiplication works, you're taking double second row and adding it to the third row and making that my new third row. Okay. So far, let's try to finish this up. So E3 is good. So we live with 2 more. What is E4 going to be? So we got E3 times E2 times E1 times A, right? We already know what this looks like. So the question is, this is going to look like what? 1, 2, 3. This is going to be what? 0, -2, -3. This is 0, 0, -4, right? So what's going to be E4? Again, E4 is just -1/2 of R2. Make that R2, right? So what would be that? Once we have that, then we have everything. Because E5 is the same idea. So all I want to do is change the second row. And I just want to scalar multiply by -1/2. So in order to do that, everything else stays the same, right? The other rows stay the same. And all I'm changing is the second row. So this must be a -1/2. And if you multiply it out, right, second row, what happens when I do this? I only get the second row being multiplied by -1/2. And then E5 is the same idea. What is E5 going to look like? I want the third row, right? The third row to be by -1/4. So I'm gonna have something that looks like this: 1, 1, 0, 0, 0, 0, 0, 0, and this is -1/4. So when you multiply these matrices on the left, what happens? When you multiply E5, E4, E3, E2, E1, right, to A, what do I get? At the result, I get RREF. I mean, no, not REF. I get REF of A. I get the row echelon form. So next time I'll explain why we care about the elementary row matrices, why we care about elementary matrices that represent elementary row operations, and how that relates to finding the inverse. So that'll be for next week. All right, guys, I went a little over. I forgot we stop at 55, right? So I'm gonna stop the